Chemistry. Everything's made of chemicals, and everything depends on chemical reactions. And that's why we chose the topic of chemistry to be this year's theme for Stormwater Awareness Week. In fact, we call it the chemistry of stormwater. And of course, that is no less true than industrial facilities. Industrial facilities are full of chemical reactions, but so is the runoff from stormwater or industrial facilities. Chemistry determines the water quality. And so why don't you stay tuned while I and a few guests talk about the chemistry of stormwater in industrial facilities. Okay, well, we're back, and thank you for joining us for this year's Stormwater Awareness Week keynote, the chemistry of stormwater and industrial facilities. And so, you know, chemistry can be kind of heavy. I was a chemistry major, I know, and if you've ever taken a chemistry course in a high school or college, you know that there's a lot of formulas, there's a lot of heavy stuff in chemistry. So we're going to take a little lighter approach this week, but we're going to look at chemistry and how it affects stormwater runoff. And to do that, I've invited a few guests, as I mentioned. My first guest is Gunnar Hendrickson with Jim Elliott Christian High School here in Lodi. So Gunnar, come on up. Let's talk about chemistry. All right, Gunnar. Well, welcome to today's show. Why don't you tell me a little bit about yourself? What year are you in high school?
So I'm 15 years old. I'm a sophomore.
Okay, have you had chemistry class yet?
Yes, I have.
And who was your teacher?
Mrs. Rash.
Yeah, and then was it hard?
I'm actually going through it right now. It's pretty rough.
Yeah, chemistry can be kind of rough. And so I know I was a chemistry major. I majored at Azusa Pacific University. Graduated back in 1986, and I think I've forgotten more about chemistry than I learned. But yes, it can be very rough. But we're not going to make it rough on you today. And in fact, on our viewers and our live audience here today, we're going to try to have as much fun as we can with chemicals. But we're going to take some really common topics. And when it comes to industrial permits, later, I know you don't know too much about the industrial and PDS permit, but later on we're going to have someone come up and talk about some of the specifics. But there are three basic tests: pH, and total suspended solids, and oil and grease. But let's talk about that first one. Gunnar, what have you already learned about pH? What do you know about pH?
So pH stands for power or potential of hydrogen. It is made up of strong acids, weak acids, strong bases, and weak bases. The strong acids and strong bases go through something called protonation, which is when they give out H+ molecules when they get put into a salt or an aqueous base or aqueous solution. And then weak bases and weak acids, they give out some H+ molecules, but not as much, and they tend to have a weaker pH.
Wow. It sounds like you're ready for that exam. Did you have a pop quiz on this recently or something?
Well,
yeah, well, right here we have some molecules here. I'm going to give you some water. That's H2O, right?
Yep.
2 H's and an oxygen. That forms water. Now, what kind of solvent is water?
So water...
It's an ionic solvent, right?
Solvent, yeah.
Right. So that means that water is going to dissociate into two different types of particles. Of course, it's still H2O, but when it goes into solution, we have. Do you know what the hydrogen's called?
I know.
Okay. Typically, it's a free radical hydrogen. It will have a positive charge, and a lot of times we call it hydronium. Now, sometimes we draw it as just a H+ like this, or sometimes I'll borrow that, because that's really what happens. Is lots of times the oxygen will borrow a hydrogen, and we'll have a 3 hydrogen molecule called hydronium. But when we get a surplus of H+, do you know what happens to the solution when we get a bunch of these?
No, I do not.
Okay, well, that lowers the pH, and we get an acidic solution. But the opposite is when we have this OH group. And so if this has a positive charge and we take it away, I'm going to give you back your positive charge, and we take it away, this will have what kind of a charge?
No, I have a negative.
A negative charge, and we call that a hydroxide ion. And when we get a surplus of these, we are going to have a basic solution, or sometimes we call it caustic. But yeah, it's going to have what type of pH number? High, right? High pH. So we're going to be higher than higher pH, and then when we have a surplus of these, we're going to have a lower pH. What's neutral? Do you know?
7 is.
7, right. 7 is our neutral area. And so a lot of people don't know that pH is actually logarithmic. And so the further away you get from 7, either to bigger numbers or to smaller numbers, you actually go up by an order of magnitude. It's kind of like if you're familiar with the earthquakes, the Richter scale, each point bigger is an order of magnitude. Same with pH. The smaller number, like when we go from 7 to 6, that's one order of magnitude. Then 6 to 5, it's another order of magnitude. So a pH of 2 is pretty acidic, and a pH of 10 or 11, pretty caustic. All right. Well, I thought we could have some fun. You want to actually get your hands wet and try some chemistry over here. So come on over to our lab. All right. Well, Gunnar. First off, we're gonna do some demonstrations on a pH. But today and this week, we're talking to the stormwater professional. And some of the professionals are very familiar with chemistry, but many are not. In fact, when it comes to pH, pretty much this is the limit of their knowledge. What is this?
This is a pH meter.
Yes, it is. It's something that we use in the field to determine the pH of liquids. Now, the very first thing we got to do before we use an instrument like this in the field is to calibrate it. So would you like to help me with that?
Sure.
All right, so go ahead and pull that cap off. And what we're going to do is we're going to use some calibration solutions. They're actually called buffers. In fact, in a little bit, we're going to talk about what a buffer is. Buffer is actually a very stable substance, which means why we can use these pretty repeatedly until they really get, visibly cloudy or yucky, But we're going to start with a pH 4 buffer solution. Then we're going to test with a 10 and then a 7. You want to start us off with a 4? So just go ahead and turn it on. There you go. Here, let's go ahead and pick that up and hit cal. There you go. And on the bottom, we're seeing 4.01 because that's what that liquid should be. And you see the 4 dropping. What's it reading right now?
Right now it's at about 4.05.
Oh, not bad. So it's actually in a pretty good solution. So why don't you hit hold? Very good. And that locks it in. There, we did 4. Give it a rinse in that water there, right next to it. Now, I like to go to the next highest. When I was in chemistry lab, they taught me to do your low, then your high, then your middle should confirm it. So go ahead and put it in there. It's ready to go. It's going to automatically know it's a 10. Look at there. It's already popping up at a 10.01. It's thinking, okay, it needs to be 10. Numbers are rising. Go ahead and jiggle it a little bit. There you go. What are you reading?
It's at about 9.39.
Okay, that's meaning we need to do a calibration, so it's good. And let's just let it stabilize for a little bit. Now, in the field, we want to let it go for maybe up to a minute or 2, but we don't have that much time here. It's actually pretty stable, so go ahead and hit hold. And set that down, rinse it again. And now we're going to go to our third, and that's a 7. And put it in there. You don't need to hit any buttons at this point. It's still in calibration mode. And it's dropping. What's it reading?
It's at about 7.30.
And dropping, isn't it? Yeah, go ahead and jiggle it a little bit more. We want to, ideally let it get to where it's pretty stable. And just give it a few more seconds. And we're at 7.24. It looks like it's holding there. So go ahead and hit the hold button. That locks it in. It says, okay, you really should be a 7.00. And now go ahead and rinse it just a little bit more. now our pH meter is calibrated. In fact, it says it's ready to go. How about we try some real acids and bases to see what it turns out. So right here, we have some what we call acetic acid. In fact, let me take that from you, set it right here. Acetic acid, do you know what acetic acid is?
That's vinegar.
That's right, so it's a fancy name for vinegar. And so it's a weak acid, but isn't it? Let's see what the pH is. Go ahead and put that in there. All right, what are you seeing?
It's at about 3.07.
3.07, is it dropping still?
No, it's staying pretty stable.
All right. All right, then yeah, look at that. It's pretty stable. So 3.07, and we probably round that to 3, to a 3. So go ahead and rinse that off in the water and set that down. Now, how about we try a caustic or a base? Way over there, I've kept it separate so we wouldn't confuse it. Be careful, we don't want to spill it. This is sodium hydroxide, which is a strong base. And what do you think the number, before we even test it, what do you think the number is? Is it going to be below 7 or above 7?
That's going to be above 7.
Above 7.
Yeah.
What do you think? What?
Maybe like around a 10-ish.
10? Yeah, probably 10 plus. So let's see what it is. And what are you getting?
It's at 11.07.
11.07.
Steadily increasing.
Okay, just let it jiggle a little bit in there, and still going up?
Yep.
Where are we at now?
We're at 11.19.
11.19. Okay, so it's going to hang out 11 plus. You know, we might get 11.2, but yeah, that's a strong base.
Yeah.
So go ahead and carefully set that down and rinse it off in our water right here, and so there we go. Now let's go ahead and turn that off and set it down right here. Now, unfortunately, this is kind of the extent of what a lot of people in the stormwater field know about as far as pH. They know, okay, I get my meter out, I know how to calibrate it, I stick it into some liquid, and boom, there's a number. But they don't understand the chemistry going behind that. And we talked a little bit about that over there, the surplus of positive hydronium ions would be more the vinegar, right, the acetic acid, or the surplus of hydroxide ions, the negatively charged, would be more that sodium hydroxide, which we have right here. Now, let's look at another way to do a pH determination. And one of it is to find that exact middle spot. Neutral was what pH?
Neutral 7.
7, right. So we call this a phenolphthalein titration. Now, we're not going, as I mentioned, we stripped out some of the heaviness of that. You will probably do this in chemistry laboratory at Jim Elliott Christian High School. You'll probably do a titration like this, and you're going to be required to do some calculations to figure out the exact molar ratios of the substances you put in there. Now, I don't think our viewers want to go there, and we don't have the time to do that, but we're going to at least demonstrate where that middle neutral spot is. So I'd like you to take some phenolphthalein here, and we only need like 4 drops. Put it in, we have a flask here of just water. Just water. So put 4 or 5 drops. It's not so important how many, but that's good. That's enough. Now, you can just kind of give that flask a gentle swirl like this when we need to. All right, and mix it in there. And then we're going to use this a little bit maybe to rinse it down. Now what we're going to do is to that water, we're going to add some sodium hydroxide. I have filled this titration tube up with sodium hydroxide, and right here we have a little valve that's closed right now. You turn it vertical, it's going to drop in some sodium hydroxide. Give it a good amount of hydrogen. Keep your valve. Use both hands so you hold the and give it some. Yeah, let it pour in there. It's going to take a while. Turn it off. All right, it's turning a color, but swish that. Give it a good swish. Okay. Well, apparently our water here is a little more caustic than what most is. probably because we're on groundwater here and I used well water. So what we're going to do is we're going to take some acetic acid, and I want you to drop in some in there until the pink color disappears. Give it a swirl. See if that pink color disappears. Give it more. It's getting lighter. This is live television. Oh, it's almost gone. Give it a little bit more. Oh, there it goes. It's just about gone. All right, very good. So, Gunnar, what that means is we are real close to where that 7 level is. See, when we add the phenolphthalein to the solution, what we call an indicator. And it's going to turn that bright pink the moment we hit 7. And so right now, because it's clear, it is a acidic solution. But the moment when we're adding a basic, a caustic, sodium hydroxide to it, we're trying to turn it, add more of those negative hydroxide ions to it. But the moment it hits 7, it's going to turn pink. So now, very carefully, using your valve, add only like a drop or two, maybe 1 drop. Start with 1 drop. You got to do it pretty quick. There you go. Swirl it. That was more than 1 drop, but all right. Add a little bit more. Let's see if we can get it to just where we can barely see some pink and it stays. I can tell you you're going to need to add a little bit more. Give it about 10 drops there. There you go. Swirl it in. You can see the pink up here. It's kind of hanging out, but it's disappeared, so we need a little bit more. We're approaching that 7. This is exciting television, isn't it? This is pretty exciting. So give it a little bit more. All right, swirl it. Oh, give it a little more.
We're getting there.
Yeah, we're getting there. Don't be afraid of it. All right. Yeah, is it going to stick? Is it going to stick? Oh, it just disappeared now. Just another couple drops. I think you're right on the verge of 7. Pretty exciting stuff, huh? I mean, think, I went to school for 4 years to be able to turn water pink. Yeah, it's pretty amazing, huh? I think you need a little bit more. All right, is it gonna do it? It'll just all of a sudden get to the point where it says, I am now 7. You're really close. Give it a little more. All right, let's try that. There you go. There you go. I think you got it. All right, that's really, really close to 7, at least close enough that we're going to do right now. Of course, when you have your class, they're going to make you do some calculations with this, and you're going to have to be like exactly on that drop. But that was great. Now, let's do another little experiment, and we're going to now create a buffer solution. Now, the thing about buffers, like reason why these are buffers, is they resist change. They don't want to change the pH. And there's lots of different types of buffer solutions. There's lots of different ways to make a buffer solution. But one of the ways we're going to attempt to do this in this class, of course, chemistry is always, you can get surprising things happen, mostly not because of the chemicals, but because we sometimes are not exact in our science. But we're going to create a buffer solution by creating a mild acid and taking a base and combining them. So the first thing I want you to do is, we're going to move this out of the way for now. I have in here, I put some of this vinegar, acetic acid, right, into here. And I have some water. And we're going to take some baking soda in here. And what you're going to do is, it's sodium bicarbonate is the chemical name. Put a good heaping, well, how about two spoonfuls in there, maybe even 3. Go ahead and just shovel it in there. All right. Yeah. All right. Now mix it up real good. Put this over here. Yeah, get it all mixed up. All right, you probably have had enough chemistry now to know what we're going to do next, right? what are we going to do with this? We're going to pour it in here.
Yep.
What kind of reaction are we going to get?
It's gonna fizz.
It's going to fizz. It's going to give off a gas, right?
Yep.
And so we're going to take the sodium bicarbonate, we're going to add it to acetic acid, and we're going to get some carbon dioxide gas and a chemical reaction. But we're basically taking a weak base here, a weak acid here, we're combining them, and we're going to create a buffer solution. So go ahead and put that in there. Go ahead and do it quickly. Whoa. Good thing we had the sink here.
Yep.
All right. So we definitely got a reaction, huh? Hopefully you didn't get your new shoes wet.
No.
All right. So what we're going to do now is let's go ahead and pour more in here. Make sure we react it all up. All right, and let's just squirt some of this out here. And now what we're going to do is pour it in here, and we're going to test the pH. Now, before we even test the pH, and we're going to use this, titration takes too long. And who wants to carry one of those out in the field? I mean, it's a real pain. You know, can you see that on the back of your pickup truck out sampling stormwater? Yeah, no. So that's why they invented these. So go ahead and turn it on. Now, before we put it in there, what do we think the value should be? We had a base, we had an acid, we combined them, we had a reaction, we created a buffer. Where should the pH be, you think?
Be pretty neutral.
Should be pretty neutral. Let's see if we did it right. Now, our method might be a little bit off, but it should be pretty neutral.
It's pretty neutral.
Wow, look at that. 6.93.
9.3.
9.6. It's even, yeah, it's hanging out right at 7. Wow, look at that. It worked. Can you believe that? Hey, let's give Gunnar a hand. Thank you for joining us. Go ahead and put that right here. Yeah, very good. And that was excellent. So we'll let you get back to your chemistry class.
Thank you.
So come on here. All right. Well, there you go. There was some chemistry involved with pH. That was a lot of fun. But our next guest is someone who will really be able to teach me a little bit about chemistry. And I've invited Grizelda Martinez from McCampbell Analytical Laboratories of Pittsburgh, California. She's going to come here and help us understand a little bit more about some of the other tests that we might have to do. So Grizelda, why don't you come on up and talk to us? So welcome to Stormwater Awareness Week, Grizelda.
Thank you for having me.
Yes, how long have you been with McCampbell Analytical?
I've been with McCampbell for over 10 years, actually. So,
Wow.
yeah.
And what do you do with McCampbell?
at McCampbell, I am the technical supervisor. I oversee all technical aspects of the lab. I work with offering my technical support to our project managers, our sales team, our analyst, whether it's, assessing the feasibility of non-routine analyses or trying to figure out why certain tests may come out with inconclusive results or results that really don't jive with each other, or conversions and calculations, things of that nature. I also spearhead the research and development department, where we, of course, are always in development mode. We want to keep up with the industry, so that's basically what I do.
Now, do you ever get to do actual chemical analyses?
I do get to do some non-routine chemical analyses, but for the most part, I stick to the books.
You're helping the others who
Exactly.
are doing it.
Exactly, I help the others
Okay.
who are doing it.
Well, I have here, we're going to talk about some of the things, how chemistry gets involved with industrial facilities. And, pH is pretty standard. We see that a lot, and we did, Gunnar did a really excellent job at helping us.
And it's a very important parameter, as it drives a lot of chemical reactions. So.
Yes. But what other types of chemistries? Heavy metals. So we hear a lot of discussion about heavy metals. What are they?
Well, heavy metals are typically classified as metal elements, of course, that are of high density. They could be really toxic at low concentrations. They are used, or have been used at least, for their conductive properties. You'll find them in pigments, anti-corroding agents, preservatives. Some examples of really toxic heavy metals that people get screened for, or industries are asked to screen for sometimes, could be mercury, lead, cadmium, arsenic, and some other heavy metals you might find even in your multivitamins like zinc and selenium that help support an immune system. So
Yeah, so they're not all bad.
they're not all bad at low concentrations. Of course, anything at high concentration is going to pose a threat to the
It's
aquatic environment.
especially when we're talking about stormwater runoff, and we're talking about facilities that may use these a lot.
Yes, that's right.
So in order to determine what heavy metals are there, what type of analyses would we run?
Well, it's going to really depend on the compound that you're testing, on the element that you're testing. There are a couple of instruments that are used in the analysis. The type of instrumentation that's going to be used is going to be based on what the method requires. We have ICP OESs, inductively coupled plasma.
I was just going to ask you, what's that
Optical
stand
emission
for?
spectroscopy, that would be the weapon of choice for samples that have high TDS because it's more robust, for samples that have high dissolved material in it, versus ICP-MS, which of course has excellent sensitivity, but you might have a little bit, because it has excellent sensitivity, it might be a little bit more prone to matrix interferences. Like I said, it depends on the test. If you're testing for mercury, for example, then you're probably likely going to use cold vapor atomic
Right.
fluorescence spectroscopy.
So we have these facilities that work with heavy metals. They might be a plating company. They might actually manufacture steel. And any zinc can even come from tire wear. So they have these. But how does it get into stormwater? And in what form? Are they little tiny pieces of metal? Or is it some other form?
Well, the thing you have to understand about rainwater is that just its volume alone, of course, it's going to be able to wash up metals in particular form, but it also has an acidic property to it that has the capability of dissolving metals too. Metals will dissolve under acidic conditions. So it depends on the contact of the rainwater making its way through the environment. If it's introduced into an acidic, receiving water or something, you might have more dissolved metals.
And that's why what Gunnar did for us was real relevant,
Exactly.
because we need to know those chemistries.
That's right. It will drive the dissolving of metals, which of course become more mobile when they're in the dissolved form. You can't just filter them out, and they'll make their way to the surface waters where they could do some real damage to the aquatic.
So what I'm hearing from you is if a facility is struggling with heavy metals, one thing they might want to look at is their pH level. And if they're tending to be below 7, even if it's within an acceptable range, but they're below 7, that could be aggravating their metal problem.
That's true, yes.
Of course, we don't want to get too caustic either, because that's got water quality problems too.
Well, not just that, but there are some amphoteric metals that will react with both acids and bases. So.
Okay, wow. So again, the forms of the metals, I know I've seen on the laboratory request sheets, there's total metals, but then there's also dissolved metals. What's the difference there?
So the total metals, of course, it's kind of as the name implies, it's going to include results for metals that are both in particulate form and in dissolved form, versus the dissolved metals. And actually the total metals, they're basically the results for total metals are produced by digesting a complete sample, an unfiltered sample. So any particles any metal particles that are in the solution will eventually dissolve into the digestion medium and be quantified. Dissolved metals, though, that is typically done. Well, it's done after the samples have been filtered through a 0.45 micron filter, and that's usually done in the field, like the true EPA recommended dissolved metals. You have to filter them in the field.
So how do you filter them?
Well, sometimes, I'm not 100% sure. I know they have like maybe syringe filters or something like that, or some filtering apparatus where they could.
So they actually push the water through a filter
and then collect it into the preserved container.
So the idea is they'll catch the bigger particles
That's
of a
right.
certain micron size, and anything
That's right.
else that gets through is basically going to be a dissolved form.
That's right. And the reason why you want to filter before you put it in the acid solution, metals are acid preserved. So the reason why you want to filter it before you put it in the container is so that you don't dissolve any particular metals, and you'll have higher dissolved metal content.
And that's what I was hearing you say. It sounds like time is of the essence.
It is, yes.
Because if we let it sit, you're going to get more going into that dissolve phase.
Or you'll be losing metals to the surfaces of the containers while they're coated and the material is appropriate for the collection of these samples. You still will have some either precipitating metals or metals dissolving into the solution.
Well, I know later today we're going to talk about in another session about good sampling practices and hold times, and all that's really, really important.
It really is, yes.
Okay, good. How about reactions that happen at, can you tell us a little bit about what is a redox reaction?
Sure.
Reduction oxidation, I guess.
Okay, I guess the generic way to think of redox reactions would be, you have two constituents that are going to be, interacting with each other with the form of either giving up a hydrogen or gaining a proton.
Mm-hmm.
When a compound is reduced, it's gaining an electron, meaning that it's gaining an electron.
Right.
And when a compound is oxidized, it's giving up its electron.
I was taught to remember it, oil rig. Oxidation is losing, reduction is gaining.
That's right.
Because, when we're in chemistry, we had to
why is it
rememorize so much.
Why is it reduced if it's gaining an electron?
Yeah.
It doesn't make sense. It's
Yeah.
a little counterintuitive. But
Yeah. But we said we wouldn't get too heavy here. So, but the point is, there are reactions happening in the stormwater and sometimes in the bottle itself.
Mm-hmm.
In fact, there's been many times I've been on a site testing with a pH probe like we showed earlier, and I actually see the numbers dropping.
Because
Is that because I got a bad meter?
No, it's the solutions reaching equilibrium. So
Mm-hmm.
the equilibrium meaning that the parameters of the solution are going to stay for at least a fixed amount of time are going to depend on the chemical reactions happening in the container.
So the stormwater professional needs to understand that there's chemistry happening all around them. And the water flowing off site, it may be, when we look at it, we're not thinking chemistry, but it is definitely a big
chemistry.
part of it.
Yes.
Okay, how about, let's move from inorganic. We've been talking pretty much about inorganic,
Mm-hmm.
which would be metals and
Anions.
pH and conductivity maybe. Let's move to organic. And I know later we're going to talk a lot more about this, but first off, when the dreaded organic chemistry class. Did you ever have to take that?
Of course.
Yes.
It's one of my favorite courses.
The Morrison
Don't
and
knock
Boyd.
organic chemistry.
I think I got one over here. Morrison Boyd, right? Remember that blue? I mean, it gave us nightmares in school, right?
It's a little hairy, but yeah.
When we talk about organic chemistry, what's the basic definition of organic
Well,
chemistry?
the basic definition of organic chemistry has to do with compounds that are predominantly made of carbon and hydrogen.
Mm-hmm.
That's what you would classify as an organic compound. Of course, organic chemicals have a number of applications in the industry, and we use them on an everyday basis sometimes.
So examples would be oil.
Oil, of course, petroleum products. You go fuel your car with gas, degreasers, solvents, nail polish remover. I mean,
But even other things like sugar. Sugar's
sugar's
organic
organic
chemical.
as well.
And alcohols.
Anything that's carbon hydrogen based.
Yeah. So
So it's the majority of the chemistry that's taking place in the real world setting.
So when in the stormwater world, there's three that come up quite a bit. One of them's oil and grease, and I know we'll talk about that later today.
Sure.
But let's look at one that's real common, and I think pretty commonly misunderstood, is something called VOCs and SVOCs. What's that referring to?
Well, VOCs, they're volatile organic compounds, which means that at ambient temperature and pressures, they will want to go from being in a liquid phase to the vapor phase. They're, of course, major contaminants in the air, obviously, because they want to go into the gas phase. They're typically low molecular weight compounds, and they're volatile because they have really low boiling points.
Now, does that have something to do with those funny vials that we have to collect them in?
It does.
And we call them VOA
You call
vials.
them VOA vials, that's right.
Volatile organic analysis, right?
That's correct. Of course, the VOA vials are designed to appropriately hold samples that are going to be analyzed for volatile.
And one of the things I know you can't have in that's an air bubble. Why is that?
Because you don't want to lose any volatiles, like we just said they do want to go into vapor phase to the headspace of the container. Yeah. And semi-volatiles, they're higher molecular weight compounds. Typically, they have higher boiling points, but they still will volatilize at hotter temperatures. The way that they're classified in the laboratory, though, is going to be based off how we analyze them. So if the sample lends itself to purge and trap, which is a process of sample introduction of volatiles, then we'll treat them as volatiles.
Okay.
If they lend themselves to liquid extraction with solvent evaporation, then we'll classify them as semi-volatiles.
Okay. So you mentioned that heat is a factor. And I know one of the things that really gets pounded to the person, the sampler, is keep the samples cold.
Yes.
That's pretty important when it comes from a laboratory's perspective, right?
Temperature controls on samples are important for a number of reasons, but of course volatility is going to be one of the major ones.
So we're not getting it to go into some headspace or something in the
You're
container.
not off-gassing it, that's right.
And I understand when you actually take a sample, especially from a VOA vial, you actually are there. If you notice, the cap has a rubber right there on top. You're actually putting a syringe into that, right?
This is why collecting volatiles in the correct sampling container, which is the VOA, is important, because the way that the samples are analyzed, it has to lend itself to a transfer where you don't have to open up the sample.
Get stuff flash out.
Exactly, and hence you'll lose volatiles.
So it goes straight from the container to the syringe into the machine.
Into the sample introduction apparatus, yes.
And how do you actually test for these organics? What kind of technology is being used to tell me I got so much
There's gonna
benzene?
If you are interested in testing benzene, it's going to depend on the constituent that you're trying to test. It depends on the technology that is the most appropriate for it. That's going to give it the best sensitivity, so you can achieve lower detection limits. SVOCs, as far as 8000 series, 8270, and VOCs, 8260, 624, they employ what's called a GCMS.
Okay.
Where the compounds are.
What's that stand for? Gas
chromatography, mass spectroscopy.
Okay.
Yes. Where the samples, there's a form of sample introduction, and the contaminants or the compounds that are found in that sample are going to be separated with a capillary column, where they're ionized in the source, and then they're sent to the detector, which is what's measuring the
Yeah.
the
I think you're bringing back some nightmares I had from chemistry lab. I remember this, and if I remember right, each of these volatile organics and even semi-volatiles have what we'd almost call a fingerprint. In other words, they're going to show up at a certain place in a certain way, and that's how you know what it is, right?
That's correct. So the GCMSs, they offer almost like a three-dimensional view of the compound. Okay. The intensity, of course, is going to tell you the concentration, where it lies on the x-axis.
The time chart, right?
Exactly, it's the time chart where it falls off on the chromatic column, and that fingerprint, which is going to give you the ultimate identification of the substance.
I've even heard of oil companies sometimes using that unique fingerprint to be able to determine whether the product was likely theirs or somebody else's. And so it's such a unique fingerprint that they can do that.
Although, you do have interfering,
Yeah.
You will have some interferences. There's not really any tests out there that are absolutely free of interference, but GCMS definitely is a powerful tool.
Well, and I guess another thing is, we're talking to the stormwater professional, and a lot of the, they maybe don't understand the dynamics of VOCs and SVOCs. But the first thing is, when they get the laboratory report, they'll notice there's a lot of names and a lot of numbers. SVOC and VOC is not one number.
No.
It's a host of chemicals, right?
And that is because each compound has a specific toxicity level. So you can't really just categorize, an overall value for VOCs or SVOCs. Why? Because you'll have compounds that have MCLs at an order of magnitude of, between order of magnitudes, in parts per million versus parts per trillion. So definitely analyzing them individually is required.
Okay, so bringing this all back to home to Stormwater Awareness Week, we have these pollutants. This time we're talking organic pollutants. How do they get into stormwater runoff? Because we're talking about things that are going to volatilize in the air. Do they
Well,
also dissolve to a certain extent?
They will. So when you think of volatiles, I mean, you'd think, well, why doesn't it just off gas?
Yeah.
Well, the problem with SVOCs and VOCs are that at low concentrations, at trace concentrations, they do form stable. They are solubilized into the water in a pretty
To a
stable
certain
fashion.
extent.
And even at those low concentrations, they're highly toxic for receiving water's aquatic life cycle.
So they, even though water is a ionic solution, as we were talking earlier, and organics tend to be a non-ionic or polar or non-polar,
Yep.
At low concentrations,
They
they
will-
will
they
almost
will
behave as ionic.
They will, only because they will have a certain level of solubility. Of course, the more soluble the volatile, take
Like
acetone.
acetone,
Take
yes.
acetone, for example. If you have a flask of acetone sitting under the hood and you come back in a couple of hours, you'll notice that the volume has reduced. You throw up 10 milliliters of acetone in a liter of water, and it'll take it much longer to volatilize just because it's really water soluble.
Okay, well, good. Well, thank you very much for coming on, and I know we got 2 other workshops today where we're going to go far more in depth, because I really think the stormwater professional needs to understand a little bit about chemistry to be able to properly manage their site. But thank you, Grizelda, for coming.
You're welcome.
All right, well,
Thank you.
I'll let you have a seat here in the audience. And so our next guest is going to be Aaron Ortiz. He's with WGR Southwest. And he is a compliance specialist, and he's someone who's been working in the industrial field for quite some time with the industrial general permit. And so he's the person who now takes these concepts that Grizelda and Gunnar showed us, and he's going to show us, okay, what's that mean for an industrial facility? So Aaron, why don't you come on up and let's talk about industrial general permits. I'm going to have you stand right here, Aaron. So welcome, Aaron. How long have you been with WGR?
Since 2006.
2006. And so you've seen quite a few industrial facilities, right?
I have.
Yeah. What types of industrial facilities do you work with?
Oh, it ranges from recycling facilities. I've worked with landfills. I've worked with metal fabricators. I've worked with rubber companies, lumber mills, all types of things, or lumber companies.
Mm-hmm. Okay. Okay. And so do you ever see chemistry being a factor when it comes to stormwater quality?
Absolutely.
Okay.
Absolutely.
Good, good. So let's talk a little bit about what a facility would need to do. Now, Gunnar from Jim Elliott Christian High School, he did an awesome job, didn't he?
Yes.
Showing us, even though we had that explosion of vinegar all over the place. But he did a really good job of showing us pH. Now, a facility that is struggling, let's start with a high pH.
Right.
What kind of facilities would have a high pH?
If they work with cement, that's the most common that I found. That they're going to have high pH because there's lime in cement, and it's a basic chemical.
So what are some things that a facility like that would need to be thinking about doing to be able to control their pH problem?
Well, we have something which what we call the Triad of Stormwater. One is source control. The second one is preventative measures, and the third is treatment. Well, let's start with source control. Especially when it comes to substances, I found when it comes especially to pH, the best way to keep pH in control is not to introduce it into stormwater in the first place.
Okay, yeah, to keep the lock and the key apart, right? To keep them
Precisely.
separated,
Precisely.
right?
Right.
Or to remove. Well, sometimes we say to remove the lock altogether, so it's not
Precisely.
even present. So we would use source control maybe by looking at alternate types of things we could use.
We could, or keep it undercover better. Try not to let, for example, if you work with dry cement, well, when you move it around, it's going to get a lot of dust off. So what can we do? Some places work inside buildings, and then they also have like plastic drop curtains, things. They also have dust collectors, things to help capture or keep it from migrating
Control the
outside.
source.
Keep the track out from getting outside where it exposes the stormwater.
Okay, and all the 3 of these, what you call the triad,
Mhm.
fit under the umbrella of what we call BMPs, best management practices, right?
Yes, BMPs.
So source
absolutely.
control is a type of BMP.
Right. And the term BMP is very broad. BMP stands for best management practices. It's my definition is whatever you do or whatever you build to reduce or eliminate pollutants in stormwater. So it's very broad. You can do everything from practices like putting up signs saying, don't pour this here because it's going to be exposed, to actually building a containment or doing it inside a building or have covers. Those are structural types. But I find often the BMPs that are really effective are just keeping a place clean. And practices. I have a former client of mine who now they got out of the permit. Good for them. They work with cement a lot. And they had problems with their pH being really high. In fact, there were times where I was working, and one of the things was they used to hook up trucks to these machines, and it would come up, and the truck drivers were in a hurry because they were paid by the load, so they'd want to disconnect when their cement trucks are full and take off. The problem is the pneumatic system for the thing would shut off, and all the cement or slag they also had would come down and hit the ground, and then they had to come by and clean it up, and now it's present in stormwater.
So we're not controlling our source in
They're
this
not controlling the
case.
source. So what they did was they just told the truck drivers, you need to stay hooked up for our system for 5 minutes after you're done unloading. So that way it has a chance for the product to get up and into the containment. And they had a vast improvement on that simple, basic practice. And it didn't have to do one sweeping job, they didn't have to do one cover or one extra containment, just stay hooked up for an extra 5 minutes. So sometimes practices, and often practices, are the most effective BMP you can use.
Now, the second type, I think you said, is pollution prevention.
Pollution prevention.
And that can be kind of similar to source reduction. How is it different? What's pollution prevention?
Where a couple of things. One, you're right. It's often source control, where what can we do to keep this from getting in contact with stormwater? But businesses have to function. And it's unrealistic to think that you're not going to have pollutants that are going to make it and expose to stormwater. So what do? Well, clean up. One of the biggest things to do is good housekeeping. That's a critical thing. Sometimes I've worked with facilities where they need to sweep once a week and their stormwater is fine. I found some facilities where they need to sweep every shift. And I have some clients where they take the last 15 minutes of their shift to clean up every day because they know they have a lot of pollutants. So it's, again, a lot more in practices. You'll find that practices are most important.
Yeah.
Keeping things clean.
Yeah, and also containment, right? Keeping
Absolutely.
things in the place they belong.
Precisely. Undercover, especially if you have dust generating things. So lots of times the dust generating things are under control because if you have paint booths or you have sanding places, often they're enclosed. Yeah. And so that is kind of a built-in containment because you also have airborne regs you have to work with.
Right, so we want to keep it out of the stormwater and keep it from being present so that stormwater could pick it up.
Exactly.
And then the third?
The third is treatment control. Again, life is not perfect. When you do a job, sometimes you absolutely are going to have some things that are exposed to stormwater, and you clean up the best you can, you practices you best you can, but no matter what you do, it's going to end up in stormwater. So what do? Well, then the third step is treatment, where you find ways of how to treat the water to try to pull that pollutant out, or help in terms of pH, help to neutralize it back to neutral or close to neutral.
Okay, so we talked about a high pH situation. That'd be like a cement company.
Right.
What type of facility might be struggling with the opposite end of the spectrum? In fact, aren't there two numbers associated in industrial general permit with pH that people have to pay attention to?
Yes, there is. For the industrial general stormwater permit, you have a range you're supposed to be in between 6 and 9 pH units. If it's below 6, it's too acidic. If it's above 9, it's considered too basic. And so people have that target they need to fit in.
Okay, so kind of like our titration, right? We want that
Yes.
nice little middle ground.
Precisely.
Maybe not as tight as that pink color, but we want that middle ground. So what kind of facilities might be struggling with that low pH?
Facilities that use acids or acidic-based chemicals are often the ones you can find it. And sometimes I have a former client where they were having low pH and they didn't know where it's coming from. Well, it's because they had a chemical dip tank they were working with. It was undercover, so it was contained. But sometimes when they're transferring, again, it comes down to practices. They were transferring some chemicals over and some would hit the ground. And then the people would walk out from underneath the containment, walk out from underneath the cover, and next thing you know, their pH started dropping, and they didn't know, well, why? And it was episodic. In other words, it didn't happen all the time. But we kind of determined just based on practices when it would happen. Oh, well, they were adding chemicals. Okay. And so it was a matter of practices. They changed what they did. They brought things closer to the vat. All those things helped to keep it out of the stormwater, and now their water went back into the neutral range.
Okay, well, Grizelda, she helped us understand inorganic chemistry and organic chemistry, and we see both of those on industrial facilities, right?
Yes, we do.
So inorganic is really sometimes hard thing to grapple with, especially heavy metals. What kind of heavy metals do your clients really have a hard time getting a handle on?
The three basics ones for me that I find all the time is iron, zinc, and aluminum.
Oh,
Those seem, because those are most often the ones that people are looking for. Now, one metal that is a particular troublesome metal in terms of this permit is copper, because it has a very low, what we call a numeric action level. It's that target number you're reaching for, you want to be below. And so if someone has to look for copper, that's often a challenge because you can find it in brake lining, you can find it in different applications. It can come from other facilities next to you simply because it's such a low number, it's going to be found in most stormwater.
right.
So, but the ones my clients often are the three bases because that's what they work with. They work with aluminum, iron especially, and zinc.
Now, Grizelda kind of gave us a clue that to address metals, we need to pay attention to our pH levels and maybe keep it a little above 7.
Right.
But what are other ways you found that your clients need to do or implement to control their heavy metal concentrations?
Well, we find that she talked about total metals, and it was really instructional. I like that. One of the things I learned, again, I'm not a chemist. He is. So when I have a chemistry question, I come to him, or I call Grizelda, I call McCampbell, and they help me a lot. But I found out something about total metals is most of the time, metals are going to be more particulate than dissolved in nature as a rule. So if you have good filtration, often you can catch a lot of those metals just in filtering. So you have something, you talked about the three basics, pH, total suspended solids, and oil and grease. Well, if you can control your TSS, your total suspended solids, many times with that you can control a large part of your metals.
Oh, okay. So lots of times the TSS number and the metals numbers are actually go hand in hand. If we
Often.
see TSS go up, we might see our metals go up.
Often.
Okay.
So when we do pollutant source assessment, which I know it's not the topic now, but many times if we have high metals, one of the things we do is we do both the total and we do a dissolved to find out, well, how much is dissolved as opposed to how much is the total. And we find dissolved is higher, then we need to find out the pH triggers, what's causing these metals to turn to solution. But that's a step-by-step, what we call the iterative process. But most of the time we find, in general, mostly particulate.
And then organic chemistry, she talked about volatile organics and semi-volatile organics. How do you see that playing a factor in with industrial facilities?
Well, one of the three basics is oil and grease.
Uh-huh.
And the good thing is, people say, well, wait a minute, I'm not a chemist. What am I supposed to do? Well, in the industrial general permit, it tells you in table 2 exactly what method you're supposed to use when analyzing it. Oh, in fact, here's a copy. This is table 2 from the general permit, and it tells you right here in this column exactly which method you're supposed to use. So you don't have to be a chemist. It tells you what to do or what chemistry to use.
And then there's another table that, depending on what type of industrial facility you are, it'll tell you what to test for.
Exactly.
But at some point or another, either because of SIC code or because of activities, they may have to test for SVOCs or VOCs.
Yes.
So let's just say there are some present in their stormwater. What kind of things are they going to implement to remove it or to prevent it?
If it's VOCs, the best way is source control. The absolute best way. Keep it in containment. Keep it from volatilizing if you can to get it out. Most of the time, if you work with VOCs or chemicals like that or SVOCs, they're going to have filtration systems already built in because of airborne regs. So your best thing is also when you have waste products, many things that the permit talks about is, well, we have waste barrels. We'll keep them under cover, keep them closed, keep them not exposed. So many times you may be done with your chemicals, you're no longer part of a process, because where you do your process, it could be well protected or well controlled. There you have the venting, you have all that stuff, but then when you're done, you put it in an old barrel and you put it somewhere else, and it sits somewhere where it doesn't have that vapor catching stuff, and that's where you're going to have your problems. So it's just as important that when you're done with something and it's a waste product, that it's controlled and covered and contained as much as when you're in the middle of the process.
Okay. And like you said, no matter how good your pollution prevention, no matter how good your source reduction, there is still a very good likelihood that some of these pollutants could end up in your runoff.
Absolutely.
And when in your testing, if you detect them,
Absolutely.
then you may end up having to put a treatment system in.
Right.
What's that look like?
Well, there's different types of treatment systems. My preferred ones is to start with more natural ones. Like if you have space or places where you can have water run through vegetation, where you have check dams to slow water down, things like that. That would be my initial one to start. That depends but also depends. If you have VOCs or other things, you may have to go with some sort of chemical treatment ones where you have a filtration media. And then that way, someone like me who's not a chemist would have to step aside to someone who is a specialty in the business and tell you what kind of, because everybody's different.
Like you might be using granular activated carbon
Or you
to
could be-
absorb.
Exactly. Or some sort of
volatiles.
resins or some side of, I have one who uses both an activated carbon and a bone char both, which are closely
Okay.
related. And then they also have resins, and some have different types of zeolite. There's different media, and you have to get a chemical professional to help you
Sure.
with that. Determine what mix of media is going to work best to address your pollutants of concern.
So it's going to be dependent on your facility, on the level of contaminants present, and unique characteristics of your flow. Whether you have a
Exactly.
pond or whether you have space to work with or no space to work with.
Exactly. So
And-
there's a
and-
combination of things.
Okay, and I know during this week, being Stormwater Awareness Week, there's actually a lot of free workshops being given just on that very topic on stormwater treatment. So they may want to check out the website and see what kind of classes they can pick up on stormwater treatment.
Well, I know I'm going to be checking them out because I'm not an expert in chemistry,
All right.
so I need to learn.
Well, thank you, Aaron, for joining us.
My pleasure.
And to being a part of this this keynote session, kicking off the chemistry of stormwater at industrial facilities. I know you're going to be giving some workshops on annual training.
Yes, I
In
am.
fact, the big secret is usually you charge for this, but this week it's free, so people might want to take advantage of that. So
Thank you.
thank
Thank
you
you.
for joining us. All right, well, that's a little bit about chemistry. Hopefully you enjoyed those hands-on demonstrations, and our guest, I had a lot of fun. In fact, I have to tell you, I had more fun than in chemistry lab, but it was a lot of fun. And later today, our next two segments are going to get more in depth into chemistry. We're going to talk about some very specific chemical issues like BOD, COD, nitrates, that type of thing, where facilities may be struggling. I'm going to invite Grizelda with McCampbell Analytical to come back. So I hope you enjoyed this first keynote session, and join us for other workshops this week. It's Chemistry of Stormwater.